Welcome to my Chapter 3 lecture. Here's your quote. How would you like to be known throughout history for making this statement? There's no reason anyone would want a computer in their home. That was Ken Olsen, president, chairman, and founder of DEC, Digital Equipment Corporation, 1977. Guess that's why they're not in business anymore. If they are, I think they got bought out by somebody else. Okay, making decisions. We've gone through sequence, one thing after another, no branching. This is the third tier of structured programming, making decisions, if statements. You've already looked at these. This is a flow chart for an if statement. This is a dual alternative if, meaning that regardless of whether this decision is true or false, if this evaluates the true or false, it does something. Okay. This is a single alternative if, meaning that it only does something if it's true. In this case, it could also be set up backwards, or the opposite, so that it only did something if it was false. Just depends on what you want to do. So a decision is commonly referred to as an if-then-else structure because a lot of the languages use that. I mean, some do, some don't. VB uses if-then-else. Others use if-else without the then, but that's just a syntax structure. It's also called a binary structure because it evaluates what's in the if, and it can only be one of two values, true or false. That's a binary structure or Boolean expression. And here's your typical flow chart in pseudocode. Notice the declarations. Can you see anything wrong with this? They're not initializing them. Bad. Okay, well, I didn't write the book, but in our class, we always initialize it. Here's your input statement. This is just a standard input. You're getting 3 inputs from somewhere. We don't know where. And then you're looking at one of the inputs, hours worked. And notice we have a constant here. 40 is our hours in week. Is hours worked greater than 40? If yes, then we have to calculate the pay plus the overtime. If it's not less than 40, it must be, or greater than 40, it must be 40 or less. So then we just do standard pay rate. And you output the name and the pay. All right, so that's basically the Boolean. If it's true, it goes here. If it's false, it goes there. That's what they mean by that. Boolean expressions are named after the mathematician George Boole, who came up with the idea. And it works great with computers because computers are nothing more than billions of little electric circuits like switches, on-off light switches. Either that switch is open, which means it's off or 0 or false, or it's closed, which means it's true or 1. There's a lot of different ways to look at it. It's a two-state switch is all it is. True and false is just perfect for computers. So that's why they adopted that. And if you think back at the old, well, they're not old, but they're becoming old, your mechanical hard drives, they use a magnetic surface, and there's either a charge there or there's not a charge there. It either puts a charge there or it erases the charge. So that's equates to binary, okay? Modern programming languages support 6 relational operators, okay? These are, let me go to the next page. Equal, test for equivalency, greater than, less than, greater than or equal to, less than or equal to, not equal to. This one, you can phrase it a different way. You have to think in terms of a double negative sometimes when you use this. There are some things that use it, like for example, to see if a web in ASP.NET, which is a Visual Studio Microsoft product, to see if this is the first time a web page has been sent to a user, they have that not equal to switch in there. But that's just something they do. I mean, you can get around that by reversing the logic, but you need to know what it is in this case. Now, there's a not operator that's different than this not equal to, all right? I'll let you go watch the movie. You have compound conditions, ands and ors. These you need to know by rote because you will see them. You have to understand how they work. This asks 2 questions, and the and separates the 2 conditions, okay? And depending on whether they're both true or one's true and one's false, or they're both false, you'll get, either a true or false for the entire thing will be evaluated, all right? An AND decision is used when data must pass two tests. And you can nest them. And also you can, like it says here, you can use nested ifs to emulate an AND. Sometimes it's better to do that, especially if you got a really complicated compound condition, set of conditions, ands and ors and nots and all these things together, maybe 15 of them. That's just not the way to go. It's better to use nested ifs to get to mimic. That's easier to read. If you just got one or two, it's okay, because most programmers will do that in quick and dirty. But also, if you don't understand exactly how these things are going to evaluate, you can introduce logic errors into your condition. So that's another reason to use nested ifs. Okay, in order for the AND, this entire thing, to evaluate as true, what's on the left, the expression on the left of this word AND, must evaluate as true, and, hence the name, the expression on the right of the word AND must evaluate as true. Both have to be true for the whole thing to be true. And this is what I mean. If you look down here, I've got x equals 10 and y less than 5. It always starts on the left side and evaluates the second one after it does this one, right? X equal 10. Well, what if x is a variable that has a value stored in memory of 5? Would this be true or false? Well, it would be false because x does not equal 10. X equals 5 or has a value of 5. That's a test for equality in this case. So this would be false. Now, there's no way under the sun that this expression can evaluate as true here. Why is that? Because both of these expressions have to be true for this whole thing to be true. Well, if the first one is false, is there a need to look at the second one? Does the compiler even need to bother? No. And that's called short circuit operations. We'll talk about that in a minute. But here's a truth table. Here's x and y. If you go back and look at my little, well, they've got it over here, x and y. All right. If they're both true, this whole thing evaluates to true. Eventually, this whole thing is going to evaluate to true or false. Remember that this has to be true and this has to be true for the whole thing to be true. So if they're both true, the whole thing evaluates to true. If x is true and y is false, it's false. If x is false and y is true, it's false. If they're both false, it's still false. So the only way that this expression, this AND operator, can evaluate as true is if both x and y evaluate to true. Okay? Short circuit. Most compilers, except for Visual Basic, do this. In the new VB.NET, there's an operator, AND operator. There's a new operator for that, where you can cause it to do it without breaking the old code. Let's see. Okay, let's go back here. If x is true, talking about short circuiting, now this is a time saver is all it is. It's not optimization, computing optimization. If x is true, or the expression over there is true, like here, then the compiler has to look at this one because this one's true, but both of them had to be true, so it can't throw it out until it looks at the second one. In this case, it goes and it sees it's false, and then the whole thing is false. However, if x happens to be false, then it short circuits and doesn't even look at y, or the one on the right, because both of them having to be true, it'll never be true because this one's false. So that's what would happen in this case. In the short circuit operation, it would just skip that second evaluation because it already knows if they both have to be true and this one's false, there's no need to look at this one. That's a short circuit operation. Now let's look at the OR decision. Okay, in an OR, either the one on the left has to be true or the one on the right has to be true. Or, hence the word or. If either one of those are true, or both, then this whole thing is true. So it's opposite, basically, of an AND. You only need one for this whole thing to evaluate as true. And the short circuit operation takes place on the OR as well, and I'll show you in a minute. Okay. If x and y are true, there's your OR statement. They're both true. If x is true and y is false, it's still true because only one has to be true. Either the one on the left has to be true or the one on the right has to be true for the whole thing to be true. Now, they can both be true and it'll still be true. All right. If X is false and Y is true, the whole thing still evaluates as true. The only way for this statement to evaluate as false is if both of these expressions come out as false. That's the only way. It's opposite of an and, okay, sort of. And the only way for an and to be true is if both of the expressions are true. The only way for an or to be false is if both expressions are false, right? Those are the kind of things you're going to have to get your mind around, but that's basically it. It's not very complicated. Ands and or have precedence. Typically, I would put what I wanted in parentheses to force evaluations of the ones I wanted, because sometimes if you got ands and ors, nots and less thans and greater thans, you know, mathematical operations have a higher order precedence than the logical operators do. So, and you'll see those being mixed together. They talk about that here. Use parentheses. Excuse me. Finally, the not operator. Pardon me. This one's easy. And don't get confused with the not equal to operator. That's different. This is and, or, and not keywords. Not true, what that does, think of it this way. It takes whatever's in here and flips it. So if I had x equal 10 and that was true, this not would make it false. So it just flips it. And there's times when you want to do that. If I had not false in here, then it would be true. It just flips the condition. So if I have some expression in here that's true, putting a not over here turns it into false. If I have some expression that evaluates as false in here, putting a not over here evaluates as true. It says it has a higher order of precedence than the and or the or. That's it for chapter 3. Enjoy.